Okay. Is it recording?
Yes.
Yes, sir.
So yes.
Yes, sir.
Okay. So you must have, you are doing this in the class. So I'll start off with the simpler topology first, which is this. Okay. So the what you did is, if you see in the lab, or for that matter any kind of like your microphone or anything, what happens is that the signal generators generate a signal which is around 0 volts. Okay. That means the voltage can be, usually it is 0 or something, okay, because they don't have any DC voltage, so it will be around 0 that the signal will swing. So the microphone generates a signal. Now if I connect directly that signal generator here, that means the signal will be swinging around 0, so 0 volts. So that means my transistor is not biased. Okay, so I should make sure that I couple the signal without causing any, without disturbing the bias point of the circuit. So what you would do in that scenario is, what you do is you would use a capacitor which is going to give you a DC level shift. Okay, so V in is here, this is Vx. So now what happens here? The signal is going, let's say 10 millivolts up and down. So this is minus 10 millivolts and this is plus 10 millivolts. Okay, then what is the swing here? This voltage is going to, I might ask in the exam or something like that, that Vx will have a value DC voltage equal to R2 divided by R1 plus R2 times VCC. And therefore, the signal at Vx is going to swing, will go up and down by roughly plus minus 10 millivolts. Now, why I am saying this roughly, it will be less than plus minus 10 millivolts. Strictly speaking, the swing at Vx will be less than the input swing, the swing of V in. So this is very important. So I'll give the reason when we go into frequency response. So please ask me this question if I forget. Reason for this will be given during frequency response analysis. During frequency response analysis. Okay, so you do this. So my point is that, so here the signal is going to swing like this. So now we know that we have found out the gain from here to here. Okay, what is the gain from here to here? Is the GM1 times RC. Okay, that is what we have seen is the gain times this thing. Now another important thing that comes into the picture is, now how do you choose this capacitor? Okay, so how do you choose this capacitor so that I get the right thing over here? I mean, I get the right gain for the desired frequency. So now in order to do that, we have to find out. Now in reality, how does this circuit behave? I'll give a brief part of the reason now why the swing is less. I'll give part of the reason right now. The second part of the reason we'll get into when we discuss the frequency response. So what happens is that this circuit can be modeled as there is a resistance looking into this node. Okay, and that resistance is called the input resistance. Now let us redraw this circuit. So the circuit, this circuit, as far as the input signal, how much reaches Vx, can be analyzed like this. So there is a C and we call it a coupling capacitor, CC. Okay, it couples the signal onto the system. Okay, and then we replace it with a resistance of Rin. So then my Vx and Vin is here. Then the change in Vin, is plus minus 10 millivolts. So change in Vx we have to find out. So here the Vx, when I'm drawing this, I will draw small Vx, means change. Okay. So what is Vx? Equal to Vin times Rin divided by Rin plus ZCC. Okay, so that means my Vx equal to Vin. What is Rin here? Rin will be R1 parallel R2 parallel input resistance looking into the base. And what is the resistance looking into the base here? It is R pi. So therefore Rin equal to R1 parallel R2 parallel R pi. Straightforward. Divided by R1 parallel R2 parallel R pi plus 1 by omega C. Am I clear? I mean, this is a complex number, j omega c. You have to do the magnitude and do this. Okay, so it will be actually, technically speaking, square of this plus this square root of this. Okay, am I clear? Now, so what does the meaning of j means? Does anybody know what is the meaning of j here? What does it do? Actually, what is the magnitude of Vx? Vx magnitude equal to V in R1 parallel R2 parallel R pi divided by square root of R1 parallel R2 parallel R pi square plus 1 by omega squared c square. Now, can you tell me, all of you, what is the physical meaning of this? And what will you see in the lab? How will you see this?
Just changes the phase.
Exactly. So this is going to delay the signal. That's all it is going to do. And this is the magnitude of Vx change I am going to see. So now if I tell you this, so watch, why did R1 vanish? R1 parallel R2 parallel R pi square. Senorita, does it, are you there in the class?
Yes, sir.
So does this suddenly things get deleted and all, does it happen?
Sir, it doesn't, but I think, sir, OneNote somehow it is not supporting some features in your case.
Okay.
Might be a compatibility issue, something you have to search and see.
Okay. Okay. Anyway, we'll see. So then this is what you are getting Vx. So now if I see this, so watch, how should you size the capacitor? So the goal is your this, if we want all of V to reach Vx, that means 1 by omega squared c squared should be much smaller than R1, R1, I would do it like this. So that means 1 by omega c should be much smaller than R1 parallel R2 parallel R pi. Okay. So that means if I know that if my signal range, if it is, let's say, a speaker's microphone, that means my range of signal is up to 4 kilohertz. What is the range of the human voice? Sorry. Anybody knows that?
20 hertz to 20 kilohertz.
20 hertz to 20 kilohertz. So now, if that means I need to pass 20 hertz signal to 20 kilohertz signal, all the way from here to here, with almost, and the swing is at 10 millivolts. The more I pass, the better is my amplifier. I'm going to get better and better output. So let's say I want to pass completely. So now, obviously what I see is that if it is as the frequency increases, this is going to get smaller and smaller. So that means my cap value is dictated by, I will put in the C, okay. C is dictated. So now I'll define the much smaller. So what is the much smaller? I'll say that much smaller is 1 by omega C. If it is at least 1/10 of R1 parallel R2 parallel R pi. Okay, if that is there, and I'm plugging in 1 by 2 pi times 20 times C equal to 1 by 10 R1 parallel R2 parallel R pi. So what is the value of capacitance do I get from this? So that this capacitance is going to appropriately do this, appropriately pass it. So how much, what does it mean? That means if I apply a 20 hertz signal of amplitude X, at least 90% of that will come over here. If I make this 100 and appropriately find the capacitor, then 1% loss in the signal will happen. Am I clear with this? Is that clear to everyone? Any questions on this? So how to find the size of the resistor? So to find proper value of CC, the coupling cap, you need the range of frequencies that need to be amplified faithfully, that need to be amplified faithfully. And that range of frequency is called the bandwidth of the signal. So F low less than F in less than FH. This is your bandwidth of the signal. Bandwidth of signal. Now, the criteria is that your signal, that means the capacitor is sized by, you put in the lower limit of the frequency times the capacitor times 2 pi to convert it into hertz to radians, should be less than, should be equal to, either you can choose 1/10 or 100th, whatever, how good you want, if you can afford that large capacitor. R1 parallel R2 parallel R pi. Am I clear? Any questions on this? Obtain the capacitor. Then obtain CC. So what is the thing that we introduced? We introduced something now, a concept called the bandwidth of signal. Bandwidth of signal. So now what is the bandwidth? Is lower frequency less than input frequency less than higher frequency. Okay, so less than equal to be more precise. If FL equal to 0, okay, equal to 0, then signal is called low pass signal. Signal is low pass signal. Okay, if FL is not equal to 0, the signal is not equal to 0 and FL is greater than 0, signal is band pass signal. Band pass signal. If FL is greater than 0 and FH equal to infinity, signal is high pass signal. Okay. without, I just wanted to introduce this so that you know how to size the coupling capacitor. So not only this, when you are taking the signal into the oscilloscope also from, we have drawn that circuit, okay, R1, R2, there is a coupling capacitor, okay, like this, RC, you take it to the oscilloscope from here, what happens? So RC is coming out here. Now if I give this directly to the oscilloscope has a zero bias, okay. The internals of the oscilloscope, if you see, there are two ways of looking at an oscilloscope. Unfortunately, I've never been. Have you guys ever been in a lab? Last semester was online. This semester is online. First year, were you here? You are here, right?
Yes.
Hello. Did you see an oscilloscope, physical oscilloscope? What happens?
No, sir.
So when you feed it to an oscilloscope, this node will get connected to ground automatically. It gets a DC ground. But there are the features. So what we do is we put a capacitor here so that here the signal is going to, you couple the signal again. So this is another capacitor. This is called CCO, coupling capacitor output. This is CCI, coupling capacitor input. Again, the size of this capacitor is governed by the same rule that we said is this thing. Okay, but that time what we have to see is what is the impedance this way. Okay, if we have to look at this impedance of the next stage. So that time this will be decided by this thing. So the goal is to make this as large as possible. So you use this capacitor to decouple the DC from the AC. Okay, so this is a coupling capacitor. So these capacitors do a DC level shifting of the signals. So you can see that signal is swinging around zero, signal is swinging around a DC voltage. Signal is swinging around a DC voltage, signal is now swinging around a zero. So they are doing capacitive level shifting. Okay, so this is how you design and cascade amplifiers. If you use capacitor, so that unless you can match the next stage DC voltage to this. If the next stage DC voltage is equal to this DC voltage, fine. You don't need to do this. You can directly connect it. Okay. So now another thing that comes into the picture is um, in 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 an actual, okay, now the other thing is that we analyze the circuit. I'm sorry. Okay. Now we might have a scenario like this also. Okay. That time the input impedance here Rn will be R1 parallel R2 parallel. What is it going to be? R pi plus
1 plus beta Re.
beta Re. Very good. So now in this expression, in the expression that we just saw, it will be 1 plus beta Re will come in. Okay, that's the only modification. But we saw that this is going to degrade our voltage gain, although it gives us bias stability. So what was the modification we did? We put a capacitor here. So we call it the CE, the bypass capacitor. We call this is also called the bypass capacitor. Bypass capacitor. Why? Because this bypasses the AC signal from RE and takes it to AC ground. That's why the name bypass. It bypasses the AC signal. So AC signal will come here and you'll say, "Arey, this is a short circuit." Just like you, if you are able to share WhatsApp answers on WhatsApp, that's like the bypass, right? So everybody is lazy. Nature has made lazy. There are few people who want to work hard. So now electron is the most laziest guy, unfortunately. Okay. and the electron will always try to take a shortcut. And we are an electronics engineer. No wonder we'll be trying all kinds of shortcuts, right? So it will see this array. This is a nice. I have a path. I don't have to really work hard. I'll go directly here because the electron has to go home to the ground. It cannot stay anywhere else. It has to rush to its home. Okay, so it will try to find the quickest way it can reach, and it sees this, this capacitor is there, I'm finding this, it will go here. So as far as the AC signal is concerned, the variation in the this thing, it will go, but the DC will certainly go through this resistor, and therefore this is the AC signal is bypassed to the ground, so this is called a bypass capacitor. In case of a bypass capacitor, Rin is again going to be the older one. Rin will be equal to R1 parallel R2 parallel R pi. Okay, with emitter, or in case of a MOSFET based source, bypass capacitor. Okay, now the final thing is that I want to discuss in a common emitter topology is we are applying a signal V in, right? But no signal source is ever ideal. Ideal signal source will have zero resistance, internal resistance. So it will have some source resistance. Okay, RS is the source resistance. Every signal generator in the world will have that. Any microphone, battery has its own internal resistance. Everything has some internal resistance. So when I am doing this, okay, and I'm connecting, of course, I have to use a capacitor now, because otherwise I'm going to mess up the bias point of the transistor. So we will put a capacitor here, CC input, and we'll put this thing. So I will draw the exact thing that we'll be using now, which gives us gain and bias stability, RE. This is R2, RC, CCO, and finally V out is this. So when we are doing this, now if I have a scenario like this, under what condition will the maximum, see this will, so I have to find V out over V in. That means the AC equivalent circuit of this will look like, I'll short all capacitors, all DC voltages will be connected to ground. So the AC equivalent circuit, I'm not drawing small signal model, by the way, I'm just drawing the AC equivalent circuit, is going to look like this. Right? What did I do? All capacitors, I shorted them. Okay. This DC voltage is connected to ground, so R1 comes in parallel to R2, and this RC also comes like this. So this is my AC equivalent circuit of this. Now, under what condition? So now I can say that my V out, if I define this as node X, then my V out over V in is nothing but V out over Vx times Vx over V in. Straightforward. We already know this. V out over Vx is Gm1 Rc. Right? So this is Q1, this is Q1. Now we have to find Vx over Vn. So to find Vx over Vn, what do I need? I need the resistance looking into the base, of course. Okay. That means I need to find, I don't know why is this one node. I need to find the resistance looking into this node. This resistance is Rin. Okay. Under what circumstance will I get the maximum gain? if this is maximized and this is maximized. Am I clear? Now, if Vx over Vn is maximized, we get maximum gain. Implying Rin tends to infinity. Now you have to appreciate why in the beginning of this, before we started amplifiers, we said that we need a few things to do. We need to solve for R out. We need to solve for GM because this collectively gives us the voltage gain. And we need to solve for Rin to make sure that this is optimal. Keep in mind, I am not saying that this has to be maximum. Optimal could be, it could be maximum, now depending on the amplifier we were trying to design. If I want to, in this scenario, okay, in this scenario, we are trying to build a voltage amplifier. Okay, sorry. So in this scenario, we are trying to build a voltage amplifier. So Rin should be as high as possible. But if I am trying to build a current amplifier, then Rin has to be as small as possible. Okay, so that's why I said that Rin should be optimal. Optimal Rin should be there. It could be infinity or it could be zero. Okay, so that is the reason why we try to quantify, because we need these parameters. So this thing got automatically deleted. Oh, sorry, this should not have been there. Okay. So now what is happening is that, so Rin should be as high as possible in this case. Okay. But in that we'll be discussing other topologies where Rin has to be as small as possible. Because of these reasons, whenever you build an amplifier, you need to quantify these quantities and prove. See, I didn't do anything, this got erased. So I don't know why this is happening. And you have to prove that these are optimal. Any questions on this? Okay, so this is whenever you build an amplifier, you need to quantify these quantities and prove that these are optimal. But in this amplifier topology, in case of common emitter amplifier, Rin should be as high as possible. in case of other topologies as we go along. Now, we have done it for a common emitter. In case of common source, what will happen? R pi is not there. So it will be just R1 parallel R2. Okay. So which means both in case of C, R in equal to R1 parallel R2 parallel R pi, and in case of common source amplifier, amp I'm making it short, R in equal to R1 parallel R2. Now we know that thus we have to make R1 parallel R2 as large as possible. Okay, this is a conclusion that we are getting from here. Now what is the ramification of this conclusion? Remember, when we are doing the bias analysis, R1, R2, and we did this thing in case of BJT. Okay, I'm not drawing what is connected to the collector and emitter. We have to, we are considering IB. That means now let's call this I1 and this as I2. Now, in this scenario, I1, IB is not much smaller than I1. Okay, so this is important. So basically, we started out the DC bias point analysis considering this is I1, IB is much, but we said that we should now, we gave a reason that why should we waste current, so we will make this as large as possible. Now, besides wasting current, we also make this as large as possible so that we get the maximum gain from the input to the output. So so I will again rewrite the reason again. Thus, increasing R1 and R2 does two things. Okay, first, saves power by not wasting current in bias branch. Maximizes gain by increasing Rin, thereby making sure that Vx by Vin is maximum as Vout by Vin equal to Vout by Vx and Vx by Vin. Am I clear? Okay. So whenever I give a source resistance, you please break up the problem into two parts, finding the gain. Do not try to find the gain. Try to use as much simplification as possible and try to find the gain by breaking it up into cascade of things and doing it in this manner. V out by Vx and Vx by Vin. Any questions so far? Any questions? Anybody? So no questions? Rishabh?
Sir, I have to try again it.
So what is it that you have to try? You just tell me if there is anything that I should repeat or Dibyendu Biswas. Are you okay? So, Abruti, Rakesh, Himadri, Senorita Shruti, anything that I should add here? Have I missed anything that you think would help understand them?
It's fine, sir. It seems fine.
Okay, so let me see if I missed anything in case of I have blended common source and common emitter. Did I miss? Next thing. Okay, so now I think we saw that there was a gain versus swing trade-off. Okay. Now, how do we overcome that? How do we overcome this? Do we overcome this? Overcome this. So, how do we overcome this? We will now discuss two topologies. One is this topology. Okay. So all of you know this topology. You have already studied this. This is actually, although it is three transistors, but it is although it is a transistor with three terminals, it is behaving as if it is a two-terminal device. Okay, it is a two-terminal device. So it is a two-terminal device. Okay. Somebody please mute Anik Mandal. Please mute your microphone. Okay, so this is a two-terminal device, all of them. This is called a diode connected device. You already know about this, right? Okay. Now we did a common emitter amplifier like this. V in. I'm not drawing the DC bias circuit anymore. I'm just drawing the amplifier, the relevant part, V out. And we did the common source like this. RC, V out. Now we saw that we have a gain versus swing trade-off. And what limits the trade-off is the fact that the output voltage drops as soon as I try to enhance the gain by increasing RC. Okay, and certainly if I increase GM, it is going to go down also because the voltage drop across RC increases. What if I replace? What is the purpose of this RC? The voltage to current conversion is done by transistor, and the current to voltage conversion is done by this resistor. So instead of doing this, I could easily replace this with a diode connected device. So I could have a topology like VCC, okay, and I could have a topology like this. Again, it got stuck. Okay, so I'll get this like this. So I will go to another page and draw the. Now, if I ask you, what is the resistance across this terminal? It is 1 over Gm parallel Ro parallel R pi, or it is 1 over Gm parallel Ro. correct? So that means the load can be replaced by a load like this, and it won't be that strongly limited to the amount of resistance. In fact, the output common mode won't be that limited to that much. It will be more defined. The swing can be a little more. So I won't get into that. So now let us see how we can build. I will draw a few amplifier topologies using that technique. Okay. So the load is like this. Okay. So this is VCC. Okay. So this is V in. This is V out. I could put a PMOS diode also like this, PNP. Same thing is possible, V in. So this is Q1, Q1, V in, V out. So please write this down. Okay. Q2, Q2. Now I can mix transistors. Okay, so Q1, M1, I could mix again transistors. This is one thing. Okay, so now what will be the maximum voltage here? It is no more dependent on this resistor. It is going to be VCC minus VBE. Correct? So the maximum voltage and the common mode voltage here is that much, because the nature of the circuit decides it. Similarly here, it is going to be that, because the nature of the circuit defines this. So these are not very good, but we can use the MOSFET things and we can decide the common mode by properly sizing this. Okay. So Senorita, please write down. We will give a couple of problems based on these four topologies. Finding the DC bias point and what is the output voltage, DC voltage, and how much swing can happen. Okay.
sir.
So we'll give a few problems based on this, because if I keep on solving, they won't understand unless they really do it. Okay. Now we have all along been.
So can you again repeat why using MOS is more beneficial than a BJT?
Basically, I would leave that to solving a problem, because even if I do it now, it will become this thing. So I would first give a problem, homework problem, or we'll do it in a tutorial. Okay, that is much better. So let me just give you the topologies for now. Okay, and then we will solve it and you'll appreciate things as we go along. Okay, so till now we have been talking of using NPN and NMOS. So now we have to draw the corresponding PMOS counterpart. So common emitter with PMOS, PNP, and common emitter with PMOS. Okay. So what we need to do is, I want to do a PNP based thing. So emitter is common. So that means V in will be applied here. Collector output will happen. RC will come here. Similarly for a PNP, you do it like this. V in, RC, and V out. Okay. You can exactly interchange the P1 and Q1 and Q2 and get these diode connected loaded amplifiers. These are called diode connected load based common emitter amplifier. Okay. Now similarly, you can have diode connected load based common source amplifier. So instead of Q1, you can replace this with M1. Instead of Q1, you replace this with M1. Instead of this, you replace with the MOSFET. Instead of this, you replace it with a MOSFET, NMOS here, NMOS here. Okay. Now, this design where you are mixing NMOS and BJT, MOSFET and BJT is called a bi-CMOS design. Most of the high-speed circuits are usually realized using bi-CMOS. Okay, that's bipolar gives you the speed and CMOS gives you the good amount of integration and low power. Okay, so a lot of these high-speed interface circuits are bi-CMOS design, and this is a simple bi-CMOS circuit. A combination of bipolar and MOSFET realizes a bi-CMOS. So a common emitter amplifier with PNP and common emitter amplifier with PMOS. This is the circuit diagram. And if I want to do common emitter amplifier with PNP and common source, common source here, this should be source. Common source with PMOS with diode connected load, you just replace this RC with the diode connected loads. Okay, so how will you replace that in case of this thing? V in. So one option is you put the NPN like this becomes V out. Second option is you can replace it with PMOS. Resistive load. Okay, one thing. So we will appreciate this by means of problems. By means of problem solving. Because if I start taking it in the class, I won't be able to finish the amplifier quickly. So we will be doing this in tutorial. Now, this is not good. Resistor was not good enough. Diode is not good enough. What is next? Okay. How can we further enhance the swing and be we can build also very high gain amplifier. So what we know that if I build a NPN with a bias voltage here and this is in forward active mode, how does this behave like? A current source. Similarly, a PNP, if I apply a bias voltage, this will also behave like a current source. Similarly, an NMOS, if I connect a bias voltage, it is also a current source. And similarly, a PMOS with a bias voltage also behaves like a current source. So these two are also current sources. If I now if one of you says that, you know what, I'll put a bias voltage here and I will do this. What do we get here? We see that the gain here is equal to, if I have Q1 and Q2 minus GM1 RO1 parallel RO2. RO1 parallel RO2. Maximum gain possible. What about the swing? If I set the DC voltage of V out to be at exactly VCC by 2, sorry, we have VCC by 2, if this is VCC, then what will happen is that what is the minimum voltage it can go? 0.2. What is the maximum voltage it can reach? Is VCC minus 0.2. Correct? So therefore, the output voltage V out DC min equal to 0.2 volts, which is equal to VCE sat of Q1. V out max equal to VCC minus 0.2, which is equal to VCC minus VCE sat Q2. Is this clear to all of you? You see a chat question. There is a chat message or something. Has anybody sent a chat or something? Uh, okay, there was some chat message probably. Please send brief solutions of the assignments. Yeah, we will upload the assignment. Once you have uploaded the assignment, we'll upload the solutions by tomorrow or Sunday. Okay, the solutions will be uploaded. Okay, now is this clear? What I have written, this statement, statement 1 and statement 2. What is the minimum voltage before this enters into saturation? VC sat, which is 0.2 volts. What is the maximum? This will enter saturation when this voltage reaches to VCC very close to, between this and this there is 0.2 volt difference. Then this base collector junction starts getting forward biased and this is no more behaving like a current source. Okay, so the PNP counterpart of the amplifier is going to be exact. Okay, so Q1 and Q2. Now MOSFET part of the amplifier is going to be okay, so V out is here and the corresponding PNP part is, so the input device is PNP and the current source load VB, V out, okay, Q1, Q2. For the MOSFET part, it is going to be the current source load is the PMOS, input device is the NMOS, V out, M1 and M2. We can make the input device as PMOS and the load as NMOS and you get V out. Now in this case, in case of the MOSFET, let us analyze the NMOS case. What is the minimum output voltage before M1 enters triode region? Can anybody tell me that? What is the output voltage at which this M1 enters triode region?
P in
It is
minus
going
VTH.
V in minus VTH, and what is that equal to? What is the name of that called? V in minus VTH is called what? VD
Overdrive
sat.
load.
Yes, V overdrive or V effective. Okay, so V out has to reach this effective voltage, minimum value. What is the region? If this keeps on increasing, M1 stays in saturation, but M2 might get into triode if this voltage. So what is the maximum voltage the output can reach is VB. This voltage can reach threshold voltage above VB, right? VB plus VTH. Then if it goes beyond that, then this enters into triode. Am I clear? So therefore, what is the difference between this and that voltage called? It is again the V effective of M2. Okay. So that means in this case the output voltage, okay, therefore the output voltage, the minimum output voltage, min DC voltage of course, equal to V effective of M1 and the maximum V out DC max equal to VDD minus V effective M2, but V effective M2 should be a negative number because it is PMOS, so I will put an absolute value around it. Am I clear?
Sir,
So I will repeat this again. Let me just write it down again. So in case of a PMOS current source load, I apply a bias voltage, and then we have this V in, V out, and before that, let me quickly take the attendance, download attendance list. Okay, so V out. So V out, again I will write V out, mean I'm again putting here, I changed it a little bit, is equal to V effective of M1, okay, V out max DC equal to VDD minus V effective of M2, but M2 is a PMOS, so V effective M2 will be a negative number, so I'll put an absolute value. So swing equal to VDD minus V effective M1 minus V effective M2. For a PMOS case, exactly same thing will hold, same equation. The input and output has been, input and the bias has been swapped. That's all that has happened. Otherwise, the same reason holds. Okay, and of course you can find the gain equal to, so this is M1 and M2. So gain in both the cases equal to GM, I will call this M1, okay, M1 and M2, GM1, RO1 parallel RO2. Any questions?
sir, why are not we using NMOS load with NMOS transistor? Is it because the gain would decrease?
How will you use the NMOS load with NMOS transistors? Tell me. Tell me the connection. So I put the NMOS input. Tell me how will you connect the NMOS load? Source has to be this, lower than this.
So yes.
So then R out is what? Looking down, RO1. Looking up is how much? 1 over.
1 parallel RO2, 1 by GM2 parallel RO2.
So your gain drops.
So that's the only reason, right?
That's the only reason. Swing also drops, by the way. You cannot reach V effective M2. It will reach VBB. Maximum value that this can reach is V out max DC equal to VB, right? VB, I don't know why it shifted. What is happening? Okay, so V out DC max equal to VB minus VGS of M2. Okay, because current has to flow through M2, so it cannot, VGS of M2 will be what? VGS of M2 equal to VTH plus V effective of M2. Okay, so this is with this, I think all the common source, common emitter amplifier is over. Okay, tomorrow I'll record a video for common. No, let me start it on Wednesday. I'll do it in person. So common gate and source follower. Wednesday and Thursday I'll wrap up. Okay. Any questions? Any questions so far?